Okay, so we're doing problems from chapter 10. Okay, this problem says an automobile starter motor has an equivalent resistance of 0.05 ohms and is supplied by a 12-volt battery with a 0.01 internal resistance. Yep. What is the current to the motor? So let's Okay, so here's a circuit. This is your 12-volt car battery. Here is the internal resistance of the battery. The internal resistance is denoted by little r. There's the load of that's the starter motor. That's the load. That's denoted by capital R. And you can see that the load is 5 times the internal resistance. Okay. As the battery is dying, what you can think of is the internal resistance is increasing. Okay. So for instance, if the internal resistance of the battery was infinite, then the battery cannot provide any more current. Okay, so that's a way of looking at it. All right. So here's another way to look at it. So what is a battery? It's a store of energy. And what you want is the energy to be supplied to this device that you're using, to the load. Okay, you see that, so this is 5 times that. About 1 in 5 of that energy is being wasted as heat inside the battery because of the internal resistance. Okay, so about 17% of the energy is wasted right now. All right, anyway. So what is the current in the motor? So the current is the EMF of the battery divided by the total resistance of the battery, total resistance in the circuit. And the total resistance right now is the sum of these two resistances. They're in series. So 12 volts divided by 0.06 ohms. And that is 200 amps. So that's quite a large current that's going through the starter motor. Yep. And then they ask you, what is the voltage applied to the starter motor? What is the voltage across this load? The voltage across the load is, or I'll write it, the voltage across the resistor R is the current in the load times the resistance. Okay, so it's 200 amps times 0.05 ohms. And that's 5 times 2, 10 volts. Okay, so what's going on? The battery was a 12-volt battery. The starter motor is seeing 10 volts. What happened to the other 2 volts? That dropped across the internal resistance. Okay, so this is the terminal voltage. Okay, now if you wanted to see more of the voltage, as this resistance gets higher and higher compared to that, you see more and more of that voltage. The terminal voltage would get higher. Okay, and you saw this in lab. As you change the load, the voltage you saw, the terminal voltage you saw was different. Okay. All right, part C. What power is supplied to the motor? The formula for power is V times I, or I square R, or V square over R. Okay, so you could use one of those formulae. And so the power supplied to the motor is, we'll say V times I. So VR times IR. The voltage is 10 volts times I is 200 amps. So your starter motor is 2000 watts. So you have to supply 2000 joules of energy per second to get your car started. Yep. Repeat these calculations using calculations for the battery connection. Repeat these calculations for when the battery connections are corroded and add 0.09 ohms to the circuit. Okay, so when the battery connections are corroded and you are adding a resistance, see that you're almost more than doubling the resistance. And so the current will drop and not as much power is supplied to the battery. Okay? And your car might not start. Okay? So I'll let you guys do that. So I will draw the diagram for you guys. So here's the battery, here's the internal resistance, here is the resistance due to the corrosion, here's the load, and so on. Okay, and you can repeat the calculation. All right, this problem says an 1800 watt toaster, a 1400 watt speaker, and a 75 watt lamp are plugged into the same outlet in a 15 amp fuse and a 112 volts, 20 volt circuit. The three devices are in parallel when plugged into the same socket. What current is drawn by each device? Will this combination blow the 15 amp fuse? Okay, so now this is generally in a AC circuit, but we're going to, this is the toaster, this is the speaker, and this is the lamp. 120 volt. Okay, again, power is V times I, or I square R, or V square R. So what we'll do is, we know the power rating of each device. Each device is seeing this volts, 120 volts. We'll calculate the current through each device. Okay. So power is V toaster times I toaster. Okay. So the current through the toaster is power of the toaster, 1800 watts divided by 120 volts. This is 15 amps. Okay. Similarly, so that if the toaster is on by itself, it's drawing 15 amp current. Similarly, the speaker, the current through the speaker is 1400 watts divided by 120 volts. So it's 11.67 amps. And the lamp, the current in the lamp is power of the lamp divided by voltage across the lamp. 75 watts divided by 120 volts. .625 amps. All right, so in this circuit, there's a 15 amp fuse here. What this fuse does is if the current, the total current is greater than 15 amps, this fuse will burn. So when the toaster itself is operating, that's 15 amps. And as long as these two guys are not turned on, you'll be fine. If the toaster and the speaker are turned on, that's too much current. The total current will be too much and the fuse will blow. Okay? And even if the toaster and this guy are on, that's 0.2625, that's 15 amps plus 0.62, that's 15.62, that'll blow. These two guys can operate together. 11.67 plus 0.62, that's 12.3, somewhere there. Okay? So when the toaster is operating, you can't turn anything on, any of the other stuff on. Okay? All right. Did you guys understand that? All right. All right, so here's two batteries in the circuit, and they're connected in the opposite direction. Here's a 12-volt battery driving a current in this direction, and here's a 24-volt battery driving a current in this direction. Since this voltage is higher, you'll have a current flowing in this direction. Okay? They want you to find the voltage across each resistor, what is the power supplied to the circuit, and the power dissipated or consumed by the circuit. Okay. All right, the way we're going to now, what you'll see is the effective voltage in the circuit is 24 minus 12. That's 12 volts in this direction. Okay. But we'll get that using Kirchhoff's rule. We'll apply Kirchhoff's loop rule. Okay, so what we'll do is we'll go around the loop like that. We'll start off here. Okay. And since this is a loop, Kirchhoff's loop rule says the following: the sum of the voltages across all elements should add up to 0. Okay. And let's say the current flowing through this thing is I. Yeah. Now, before you apply this, how many terms will be there in this summation? As many. No, there'll be as many as elements in the circuit. 1, 2, 3, 4, 5, 6, 7 terms. Okay. All right. So we're going to go across this element. You're going from low to high voltage, so that's plus 24 volts. And then you're going from current flows from high to low, so it's minus IR3. Again, you're going from high to low voltage, minus IR2. High to low, minus IR1. What is the next term?
12-volt battery.
Okay. You're going from high to low. The change in voltage is minus 12 volts. And then again, you're going from high to low, minus IR5. Minus IR4. Okay. So this is 24 minus 12. 12 is I times R1 plus R2 plus Remember I said at the beginning this is effectively a 12-volt battery, and all those resistors are in series. I times all those resistors in series. Okay? So the current in the circuit is 12 volts divided by the sum of the resistors. And the sum of the resistors are 10, 20, 30, and 10, 30, 40, 50, 60 kilo ohms. So that's 5.2 into 10 to the minus 3 amps. 0.2 milliamps. So that's the current across in the circuit. And then they ask you find the voltage across each resistor. The voltage across each resistor is just that, I times the resistance. So you can find that, okay? So, so for instance, voltage across each resistor is I times Ri. So V1 is I times R1, and I is 0.2 milliamps, and the resistance R1 is 10 kilo ohms. Kilo is 10 to the power 3, milli is 10 minus 3, so those two cancel each other, okay? And 10 times 2 is 10 times 0.2 is 2 volts. Okay. So the voltage across this resistor is 2 volts. Okay. And again, the current is flowing this way, so this point is 2 volts higher than this point. Okay. And so on. So let's make sure. Remember, the effective voltage is 12 volts in this resistor. Across each 10 kilo ohm resistor, you'll get 2 volts. 2 volts, 4 volts, 2 volts, that's 8, plus 2, 10, plus 2, 12. Okay. All right, so we will set up this circuit in lab next time, okay? Except that we will have this battery in the opposite direction. So let's solve this, okay? So here's a typical Kirchhoff's rule problem, okay? So you have multiple sources in different loops, okay? You have I2, I3, and V1 are the three unknowns. Okay? So you'll need 3 equations to solve this. Okay? So we'll use these 2 Kirchhoff's rules. What does this rule say? The currents flowing into a junction is equal to the sum of the currents flowing out of the junction. So we'll look at this junction. Okay? Now, there are 2 junctions in the circuit, this one and that one, but these 2 junctions are on the opposite ends of the same arm, so they give the same equation. So all will do is apply the junction rule here. I1 is flowing in, and I2 are flowing. I1 and I2 are flowing in, and I3 is flowing out. So I1 plus I2 equal to I3. Okay. I1 is 2 amps plus I2 equal to I3. There's equation 1. Okay. And you need 2 more equations, and we'll apply the loop rule. Okay. All right, how many loops are there in this circuit?
3.
3. 1, 2, 3. So you can choose two of those 3. Okay. I'll use loop 1 and loop 2. Okay. So let's apply the voltage rule to loop 1. Okay. We'll start here and go around like that. Okay. All right, so we'll start here. This is plus V1. And then you're going from high to low. So this is I1 times R. Is that R1? Yeah. So I1 minus I1 times R1. Okay. And then you're going against the current, so you're climbing uphill. This is at a higher voltage, so it'll be plus I2 R2. And now you come back to your starting point, so this should add up to 0. Okay. So V1, I1 is 2 amps, so that's 2 R1, and R1 is 12, so that's minus 24. And then I2 R2, R2 is 6 ohms, so plus 6 I2 equal to 0. There's equation 2. Okay. Now let's apply this to loop 2. All right, I have difficulty with this. Who's going to help me with that? Again, we can start here. Who wants to try this? Go ahead.
So it would be positive V1, right?
Very good.
Minus R or I1 R1, right?
All right.
Then plus V2.
Very good. Plus 21.
Then minus I3 R3.
Yep, I3 R3. And you come back to the starting point. So this, yep. All right, so V1, I1 R1 is minus 24 plus 21 minus 5 I3 equal to 0. There's equation 3. All right, so now you've set it up mathematically, and now it's a matter of doing a little algebra. Okay, so let me gather all these equations. So, well, actually, I'll just all right, so okay, we can actually clean this one up. So V1 minus 5 I3 equal to 3. That's equation 3. So and this is V1 plus 6 I2 equal to 24. this is I3 minus I2 equal to 2. All right, so now we have 3 unknowns and 3 equations. And again, what you want to do is sequentially reduce it to 2 equations and 2 unknowns, and then eventually 1 equation and 1 unknown. Okay. You guys have learned of several methods to solve this. I don't know if you guys have done determinants yet, but you can do that. But here's what we'll do. Okay, so what we'll do is see in this equation here you have V1 equal to this, so we'll get, okay, we'll subtract this equation, this from that, so V1 will cancel. So 2 minus 3, equation 2 minus 3 will give you 6I2 plus 5I3 equal to 21. Okay, that cancels, this becomes plus 24 minus 3 is 21. So we'll call this equation 4. Okay, now you can see that these 2 equations, you have 2 equations and 2 unknowns. Okay, so what we'll do is we'll multiply this by 6 and then add these 2. Okay, so 6, 1 plus equation 4. You guys understand? So this would be 6I2 plus 6I2, that would cancel. Okay, so 6I3 plus 5I3 is 11I3. I hope you guys are following this. And 12 plus 21 is 33. So I3 is 3 amps. So I3 is 3 amps, so I2 is 1 amp. If you put that in 2, I2 is 1 amp. Okay. And then to calculate V1, V1 is 5I3 plus 3, so that's 18 volts. Okay, so we have solved the circuit. Okay, again, solving the circuit in this context means finding the unknowns. There were 3 unknowns: the voltage of the battery, and so on. Okay, and so we found the 3 unknowns. I3 is that current, I2 is that, and V1 is this. Okay. Now in our solutions, we got all the currents to be positive. What that means is the assumption of the direction of the currents was correct. You could have set up the equations with I3 being in that direction. Had you set up the equation with I3 being in that direction, what would you have gotten for the answer?
Negative for the same thing.
Yeah, negative minus 3 amps. That's what you would have done. Okay. Very good. All right, so these 2 rules, Kirchhoff's 2 rules, allowed you to solve these equations. Okay? And you'll do a whole circuits course based on this. Okay? In your junior level. You'll learn a couple more equations. You'll learn tree to delta diagrams and stuff like that, but you'll get there. Okay? All right. Any questions on that? All right. So again, a little more complicated. Okay. So there are 3 unknowns, and what you need is 3 equations. So there is V1, V2, and where is R4? R4, there is R4. Okay. So there's one junction, and one junction, two junctions, three junction. Here's a fourth junction, but that's on the opposite end of the same arm. Okay. All you need is three equations. You could apply 1, 2, 3 junction rules, then you could apply loop rules. There's several loops. 1, 2, 3, 4, 5, 6, 7. Okay, there's more equations than you know what to do with. Okay. All right, so okay, to get voltages, you'll need to apply the loop rule. Okay, so V1, V2 will apply loop rules to that, and then R4. Where is R4? Yeah, R4. So let's apply three loop rules. Okay, loop 1, loop 2, loop 3. All right, for this loop will start off here, for this loop will start off here, for this loop will start off here. We'll all start from the left corner. Okay, who wants to do loop 1? We'll start here. I'm sorry? Okay. Minus I1 times R1. Mm-hmm. Zero. Mm-hmm. Okay, so V1 minus 24 minus 6 minus 12 equal to 0. V1 is 3042 volts. Okay. Loop 2. Who wants to do loop 2? We're starting at the left corner. So, okay, V2
minus I3
plus
I3.
plus I3. Very good.
Then we're doing minus
Very good.
I5 R5.
Mm-hmm.
X per V.
So that's 0. Okay. So V2 equal to plus 6 minus 12 equal to 0. So V2 equal to 6 volts. Okay. All right, loop 3. Who wants to do loop 3? No, not you, Eli.
V2 minus 12.
Hang on a second. Loop 3, you're going this way?
Yeah.
Okay. So let's erase this. Okay. So V2,
Minus 12.
no, let's do,
I2 R2.
mm-hmm.
Then plus I4
Mm-hmm.
equals 0.
Okay, so V2 is 6 volts, I2 R2 is minus 12, and I4 is 1 plus R4 equal to 0. So R4 is 6 ohms. All right, so again, whatever unknowns you have, you apply either the junction rule or the loop rule, okay? And it enables you to solve these problems. You're trying to fall. All right. All right, so we'll do a couple of RC problems and then we'll get done. Okay, this has more parts to it, so let's do this one and then the last one. Okay, so this problem says a 500 ohm resistor, an uncharged 1.5 microfarad capacitor, and a 6.16 volt EMF are connected in series. So what is the initial current? Okay, so if you look at your equations notes, okay, so they don't show you a switch, but I'll draw a switch. Okay, so if when you close the switch at time t equal to 0 and the initial charge was 0, the way the capacitor charges is the final, this is the maximum charge on the capacitor, 1 minus e to the power of minus t over tau. Anybody remember what tau is?
Time constant?
Very good, my friend. So that's the time constant of the circuit. And the time constant of the circuit is the time scale in which things change. Okay. The time constant for an RC circuit is RC. So let's calculate this. This is 500 ohms times 1.5 into 10 minus 6 farads. Okay. So that is 0.75 into 10 minus 3 seconds. Ohms times farad is seconds. And the way I got that is this is 0.5 times, 0.5 times 10 to the 3. I borrowed 10 to the 3. That became 10 to the minus 3. 0.5 times 1.5 is 0.75. Okay. So things change over a time span of 0.75 milliseconds. So all these things happen very fast. Okay. When you close the switch, what this means is in 0.75 milliseconds, this gets 65% of its maximum charge. In another 0.75 milliseconds, it's up to 90% its maximum charge and so on. Okay, that's what that means if you calculate all of this. Okay, so that's the time constant of the circuit. Okay, you blink and things have already changed. Okay. So what is the initial current? Now if you look up your notes, current is I naught e to the power of minus t over time constant, and the initial current is just the EMF of the battery divided by the resistance of the battery. So I0, the current at 0 is E over R, as if the capacitor was not there. Okay, 6.16 volts divided by 500 ohms. So the initial current is 12.3 milliamps. Okay? And this is, we've already found the time constant. What is the current after one time constant? What does that mean? What is the current after one time constant? Very good. So we would put 0.75 milliseconds there. Okay? So IT is E over R e to the power of minus t over tau. Okay, so they want you to find the current at one time constant E over R e to the power of minus tau over tau e to the power of minus 1. So it's E over R 1 over E. Okay, and just to show you this, so calculate this. So this is 0.37 E over R. See, that was the initial current. After one time constant, the current has dropped to 37% its initial value. Okay, and so on. And after second time constant, it'll be 37% of the remaining current. Okay, and so on. So that's what that means. 0.37. The initial current was 12.3 milliamps. And then D, what is the voltage on the capacitor after one time constant? Okay, so voltage on the capacitor is, remember, capacitance, charge, and voltage are related like this. What this says is the capacitance is the charge at this time divided by the voltage at that time. Okay, so the voltage is QT over C. Well, what is Q? Q as a function of time. There is this expression. Okay. So the voltage is so the voltage across the capacitor is the maximum voltage in the circuit, or the voltage of the battery minus 1 minus e to the power minus t over tau. At t equal to infinity, the voltage across the capacitor will equal the battery voltage. Okay. What you're trying to find is the voltage at one time constant. So it's the voltage of the battery 1 minus 1 over E. Okay, so let's evaluate this. After one time constant, the voltage has increased, is gone up to 63% the battery voltage. Yeah. That's what it's charged to. So the voltage across the capacitor at time constant is 0.63 into 6.16 volts. All right, let's do one more problem. Using the exact exponential treatment, determine how much time is required to charge and initially uncharge a 100 picofarad capacitor through a 75 mega ohm resistor to 90% of its final voltage. Okay, so again, so RC, this is 100 picofarad. This is 75 mega ohms. Okay, so 90% of its initial voltage. Okay, you just saw that the charge across the capacitor is CV 1 minus e to the power of minus t over tau. The voltage across the capacitor is, we'll call that V naught, so there's no confusion, is V naught, again, QT over VT. Okay. So VT is QT over C, so that's V naught 1 minus e to the power of minus t over tau. At t equal to 0, that's 1. 1 minus 1 is 0. The voltage across the capacitor is 0. Okay. At t equal to infinity, this term is 0, and the voltage across the capacitor is just the battery voltage. Okay. All right, they're asking you, using the exact exponential treatment, determine how much time is required to charge an initially uncharged 100 picofarad capacitor resistor to 90% of its final voltage. Okay, so you want the voltage to be 90% of the final voltage. Okay. Which is this should be V naught times 1 minus e to the power of minus t over tau. Okay, so what you want is this to be 0.9. So 0.9 equal to 1 minus e to the power of minus t over tau. E to the power of minus t over tau equal to 1 minus 0.9 equal to 0.1. Okay, how do you solve this equation? Mm-hmm. Okay, so how do I delete this? Okay, so at this time, the voltage has risen to 90% its maximum value. And the time constant for this circuit is minus RC log. Yep. R is 75 mega ohms. C is 100 picofarads. Okay, and so this works out in, so T is, so what we'll do is, this is 100, we'll bar, that's 10 minus 3, so minus 7.5 log 0.1 into 10 minus 3 seconds. And so 17.3 milliseconds. At 17.3 milliseconds, the capacitance is charged to 90% its maximum value. Yeah. All right, well, also let me do the time constant here just as, so time constant is RC equal to 7.5 milliseconds. All right, guys, so you guys take